All right, cool. I'll keep this one quick since we're at the end of the day. So my name is David Lindenbaum. I'm from CosmiqWorks, which is an In-Q-Tel lab representing. I've got two coworkers over there, the director, Ryan Lewis, and the principal data engineer, Jake Schermeyer. So we're going to talk about a couple things. First, a little bit of what CosmiqWorks does, then go into SpaceNet, which is a partnership that we have with Digital Globe and Radiant Solutions, and then kind of my thoughts on how SpaceNet and STAC and ARD intertwine. So very quickly, In-Q-Tel is a 501c3 founded in 1999 as a nonprofit that acts as a strategic investor for the U.S. intelligence community. Our goal is to identify, adapt, and deliver innovative technology solutions from startups to support the missions of Central Intelligence Agency and broader U.S. intelligence community. Really, what do we do for CosmiqWorks? CosmiqWorks focus on supporting end users and practitioners, GIS professionals, and machine learning researchers. And we do that in a bunch of different ways. So one of the things we do is research projects on our own. So working with data, we've kind of interacted with all different types of scene classification, object detection, and segmentation algorithms, artificial colorization algorithms, and done mostly extensive performance studies. We also really focus a lot of our work on SpaceNet, which again is a partnership we'll get into. And then we do strategic assessments of the remote sensing and commercial market. One of the things we really like to characterize is the machine learning environment and really model robustness for these new deep learning algorithms. How are they actually going to react in the real world outside of their test cases? So when we really think about it, we look at spectral diversity, data resolution, temporal variance, and we try to build a manifold. If you look at it, though, we kind of have two areas where SpaceNet competition builds out. And really, that's one in building out labels and metadata. So we figured if we needed to make data sets for ourselves, we should open source them to the community so that they can learn. And then on the other side, we actually release the models afterwards. So that's another input into the open source community to actually understand how to apply deep learning models to new data. So a little bit of an example of really what's the SpaceNet's mission. So it's a partnership initiative that fosters research and innovation in the development of machine learning algorithms to automatically extract information from remote sensing data. As we said, it's an open partnership. If you're looking to get involved, we welcome new partners. Right now, it's CosmiqWorks, Digital Globe, and Radiant Solutions are the three main partners. So at the bottom it's an open data repository hosted on AWS. So it's free to download. You do need an AWS account, but if you just go there and look, open data set of WorldView 3 satellite imagery with building footprint and road labels. Next, we release a bunch of tools. These are all open source Python tools. These are really meant to help translate from a GIS world into a machine learning and data scientist world. They're ways to help people not have to answer the question of what a projection is and just get to a NumPy array. Next thing we do is we publish all the code up on GitHub. You'll see all our codes there. We also publish all the winning code. So we run competitions on all these different data sets. It's a way to formalize, both making sure that we're producing real data sets that are useful, but as another thing, it's a way to actually measure performance so that hopefully practitioners can look at the state of the art in the computer vision community and realize when is it time to pull an algorithm into production or start working in that space. So we run competitions every year. They have cash prizes, and the results from those competitions are open source algorithms for the community to use. So the data set right now, the data set is 4 major cities: Las Vegas, Paris, Shanghai, and Khartoum. There's over 300,000 building footprint polygons and 8,000 kilometers of roads. Those are centerline road drawings with metadata including pavement type, how many lanes are of that road, things like that. In addition to the labels, it's the full WorldView 3 image strips that are up there for Las Vegas, Paris, Shanghai, and Khartoum, basically at an Ortho 2A level. And so that's kind of an interesting question to talk about with ARD and really where should we be interacting, what data should we provide to make it available. Again, it's all available publicly on AWS. Feel free to download it. So at the top, what's that data actually look like? SpaceNet data is source data. So we have the panchromatic band. We have the 8-band multispectral band. We have a 3-band pan-sharpen that came from the Digital Globe factory. Now we actually have an 8-band pan-sharpen that came from the Digital Globe factory. What we do then is for the competitions, we chip that down because no machine learning person actually is going to work with a megapixel image. So we originally for buildings put it at 200 meter chips. So it's about 650 pixels on a side at the high resolution. And for roads, we made it at 400 meters. So now we we broke this large image with these geospatial polygons and line strings, and we broke it down into nice chunkable things for machine learning groups to work with. And then we ran competitions on it. So SpaceNet 1, we ran in November 2016. SpaceNet 2, we ran in, we ran in June. And then we actually ran another one just in combination with Deep Globe and CVPR on the same exact data. And then SpaceNet 3, we launched in November, and that was focusing on roads. And in the future, September, we're going to launch an off-nadir imagery analysis challenge. So this is actually going to be, instead of using one WorldView 3 strip, it's how do you actually respond to 27 different images of the same exact location that are slightly different? And how does a machine learning algorithm that's trained on one transfer to the next? And then SpaceNet 5, we're going back to roads. So a lot of progress on roads, but we've seen that continuous focus on that is an important part for the general community in building foundational maps. So look forward to more data coming from there. So that's kind of what SpaceNet is. All the code is supported. You can go up to github.com, look at SpaceNet Challenge. You'll see all the results from all the competitions. Encourage you to look at it and take a look. So here's where I get kind of interested in talking about ARD and STAC. So a SpaceNet study on how do you go from 200-meter chips to 900 square kilometers of buildings. So on the left is the labels for a 200-meter chip of building footprints in Shanghai. And on the right is over 900 square kilometers of building footprints created automatically over about 6 hours on the same image strip. It's on the cog map. So it's loading an MB tiles layer. There's a cog underneath it, because if you try to load this in QGIS, it will crash. So even talking about big data like that, how do I enable non-GIS people to use and explore the data in an intuitive way? Cog and STAC, and this is something I'm really looking forward to exploring more. Links on the bottom, you actually can see there's a STAC catalog there. On the right is the cog map labeling. Sorry, I didn't get around to getting better names for the links. And then actually the code for how to create this whole entire stack is all there in GitHub along the way. So from a stack perspective, we looked at one interesting thing. So how many different files did it take to go to 900 square kilometers of building footprints? So it took a pan band, a multispectral 8-band. It took a pan sharpened 8-band. It took source labels, which is an area of interest. It took building footprints for that labels. And then it took a labeling schema to actually get that labeling done right. Then we put that down. So now I have to tile that up in some sort of way using some code to put 200-meter geotiff tiles and GeoJSON labels. That's the first step. Then I have to transfer that type of geospatial label into a machine learning label. So that's going to either be in some sort of JSON format or another meta language or a protobuf format or a raster mask in a PNG. So all these different ways. I'm going to shoot it over, and now I'm going to create a model. That's got weights, it's got a structure, it's some random Python code, honestly, that's not very well prepared. And it has both image transformation code for how to take a 200-meter chip and go into it, and image transformation on the after effect of how you take the code and go out. And then after that, I can think of some way that I'm going to tile and recombine all these 200-meter chips together and pump out an answer on the top. And at that point, I have a GeoJSON layer. Hopefully, if I'm going to actually let people look at this layer, I need it to be in some tiled web format. And I need to know the different transformation layers because I want to be able to inspect and understand where my machine learning algorithm went along the way. So not only the final product, but the intermediary steps so I can explore where it went wrong and think about how to do better. So that's probably about, 10 different data formats, all that kind of need to be cataloged and tracked. Because if I want to reproduce the work, I need to know where it came from. And so I started with CosmiqWorks 4 years ago. We've been collecting geospatial data for machine learning for the last 4 years. I really want a catalog that's searchable by new scientists that come on board. And so that's why I'm interested in STAC, for being able to track that. And so visually, I think visually this is an interesting way. So the top blue up the top on the left, the yellow is the full WorldView 3 strip. The blue is the area that we actually labeled in there. And you can see the little green footprints inside that are actually actual footprints. We break that down into tiles. And then on the other side, after a 2-month competition, when someone open sourced a code algorithm, I'm able to pump out for the whole entire image strip all the building footprint labels. And if you go to the website, you'll actually see that they're pretty accurate. This is starting to get to be usable. So really, it's kind of how do you go from 200 meters to 900 square kilometers. But then if we talk about ARD, what's analysis-ready data? So this algorithm was used on the 8-band pan-sharpened data that came out of Digital Globe Factory. I can't reproduce it with GDAL. And just as a little bit of an example of why this is important from a standardization perspective, same algorithm, same math, same exact code. So blue underneath is what came out of the Digital Globe factory, and green underneath is my own creation of the pan band and the 8-band multispectral. Same algorithm, slightly different data input, very different result. So from our perspective of understanding what data to let someone work on, that's an important step. Now, we learn every time, but retraining this algorithm for each data set, that's a costly endeavor. So hopefully I can transfer that knowledge. But I thought that was kind of an interesting point to put on from a machine learning perspective of why ARD matters to us. So that's kind of it, except just to say that for us, SpaceNet 4 and SpaceNet 5 are happening this year. If you're interested, please get involved. Let us know. The code's all up there, and if you're a company that wants to become a partner, please talk to us afterwards. And then future CosmiQ areas, we're always working on new things, so exploring multi-resolution imagery, how to combine non-imagery data sets with imagery itself, and then how to interact simulated data with other data. So those are kind of what we're working on for the next couple of years, but looking to get involved. So thanks.
I have a question. So you bring up a really interesting point here, right? Which is the sensitivity of the analysis you do downstream to, let's call it variance in the data, right? In this case is source or processing variance. And so I think this is one of the most interesting things to start thinking about standardizing in terms of establishing benchmark data sets and reference implementation. So we could unit test against the variability due to the source of data, right? I mean, so it's what it means to be interoperable. It means it should be invariant to the source, right? And so now what we need to think about is machine learning that is interoperable and agnostic to the source, because what is it picking up that is not an object on the ground? It's obviously some artifact, right?
Yeah. So I think that's a really interesting question, and one that I think what is great about having the SpaceNet algorithms out there is that we can actually test some of that invariability. That's one of the areas in CosmiQ that we always focus on, is not only where it works, but where it breaks. And so I don't know whether you can get to that level of interoperability, but knowing that it's there is important. Also from our side, if we're gonna run a competition on data that is not standard, then that means the algorithm can't expand to somewhere else. So for our perspective, getting to an ARD standard is helpful to serve the imagery up, because then we'll focus people towards that. But someone mentioned before, I believe you did, about having benchmark data sets. And so that benchmark data set thing is a key component of SpaceNet that we've been focusing on for the last 2 years. So one of the things we do in addition to the SpaceNet challenges on the SpaceNet data repository is we actually host other people's data sets that they've built. So there's 2 IARPA challenges, there's a SOCOM challenge. We're open to more data sets coming in for people who want to explore with that data. And that's why one of the reasons for the STAC catalog, because I can't update things as quickly. So if I can figure out a way to let people explore the data set themselves, that's really beneficial. And really our goal with SpaceNet is to enable everyone to do better work and do good answers. So get good answers.
Yeah, so that was, first of all, a really awesome talk. I was interested in, so the difficulty you had reapplying the results that you made.
Mm-hmm.
The sophistication of some of these deep learning algorithms, picking out caps and all sorts of codes and stuff, sort of suggests it's able to do that if given the right input, right set of input data. But as some of the other people have been talking about their new satellite systems, it's these satellites are more laboratories than cell phone cameras, right? And in a situation where you have one large strip from Digital Globe that's been cut up into however many different tiles and has like millions of different labels on it, the variable parameters of like what specific off-nadir angle was there, the general state of the atmosphere on that day, et cetera, where the sun was. Like, it seems like you have, a few examples of that. So is there any way to like, it seems like it's just an astronomically large amount of work in the current state of affairs to use, 200,000 strips, right? As opposed to
Yep.
as opposed to one strip that's been cut up. But that's kind of what's needed in order to take a machine learning algorithm.
So I think there's a good point there. So on one side, yes. So going to scale is a tough problem for a machine learning algorithm. On the other hand, the amount of time it would have taken humans, a group of 10 people, to label that 900 square kilometers of area would have been, it's probably measuring in months as opposed to hours. So on one hand, not to be a downer of that, like you can actually expand and extrapolate out from labeling a small area of a single image and go farther. On the downside, you're right, though, definitely that there's more variability to be there. I think that's actually where SpaceNet 4, where we're focusing on, is the multiple different images that will have slightly different perspectives to hope produce some of that variability into the algorithms. Because I think it's as much I don't think it's necessarily a weakness in the algorithm as much as a weakness in the training data in this case. SpaceNet, we will continue to try to push more data out there to help people explore that. And then I think that's a conversation also on how we build even larger data sets and understand that variability.
I would just request that you like bug this guy and that about delivering, 200,000, even in small sections of 200,000 strips, because
Yep.
I think they need that pressure, and actually they need to be able to apply that pressure.
I will say we have a great relationship with Digital Globe and Radiant Solutions. We're very good friends.
Yeah.
Yeah.
We plan to do one on clouds so that Farmview can.
So interesting story. When we first started building footprints, which I think everyone here will accept is a hard problem, we worked with a well-known organization that does open competitions, and we spent 2 weeks trying to figure out how to build a tiebreaker for what happens when everyone solves this problem perfectly. Because how are we going to decide 1 versus 10? I'm not kidding. So we skipped clouds initially because we thought everyone had a good handle on it. Now that, hearing enough of that discussion, it's definitely up there. And we'd be happy to figure out a way to start thinking about that. Because clearly, at a scale problem, clouds is still a problem. And so that's good feedback for us to understand of that. And while it's interesting because it's not necessarily a data product that an end user necessarily cares about, right? But if it enables the whole entire community to build a better product, then they really do. We will be looking into it because we thought it was somewhat done. And we're sorry.
Yeah, I suppose comment and a question. We're about to apply machine learning across 1.8 million square kilometres of 80 centimetre imagery, which is probably not analysis ready to the standard that everyone wants here. And I guess what your comment as well, that's what we're finding is that as we see different strips with different levels of DRD, the more of that you put into the training, it takes too long to train, but then you just need to smudge the error over everything you're doing, which is kind of cool. But my question was, why 200? Because you've got, GPUs, you want to fit the right amount into.
So 200 was done 2 years ago. And so if you actually talk about, if you're talking about object detection or scene classification, you talk about what AlexNet works on, it's a 226 by 226 pixel image. So we wanted to keep it at an area that wasn't going to break the existing frameworks. Frameworks have gotten a little bit better in for example, the memory of GPUs has gotten higher, but at the same time, they still work on small chips. And so we wanted to stretch them a little bit because we didn't want to go down to that, but we didn't want to make them go on larger chips. So it's a 650 pixel, 200 meter chip. We actually went for roads. We went up to 400 meters because we thought a road network needed to be a little bit more complex. And so there's some balance there of understanding how much work to put on a computer vision expert, where we don't want them to think about geospatial problems. But if we let them forget about them too much, then it doesn't become a useful product. So kind of a balance. Keith.
Just one more question, really. I'm interested in exploring maybe another SpaceNet down the road, where resolution matters. It's great, to get 3 centimeter imagery, but as we're kind of hearing here, you're shrunk it down love to see a challenge set saying how coarse in resolution can you go to before it starts to fall apart and become unusable.
Yeah. So you hit on a good point of actually what's not actually part of our SpaceNet challenges, but actually part of core cosmic work. So that's an area we've been exploring for the last 2 years, 3 years. If you go to our blog, it's the downlink on Medium with a Q, not a K. You'll see an article from my colleague Adam Van Eden, who talks about YOLT and actually talks about car detection going from 15-centimeter aerial imagery artificially degraded all the way down to 5 meters. So with SpaceNet, we can start doing that with these data sets, because if we have high-resolution imagery with a high-resolution accurate label, we can artificially degrade and start looking and exploring what it looks like as we remove information from that image. One of the things we found is that providing accurate labels on lower resolution imagery is a really tough challenge. So probably the threshold of detection is different than the threshold of human labeling at an accuracy perspective. And so, for example, when we worked with Planet Data at one point, looking at a crowded harbor, not the big ships, but the small ships. Now, a 50-foot vessel, we probably could look at and see in Planet Data, but 20 50-foot vessels stacked next to each other, that starts getting very hard for a human to actually count on their own. But if we look at a DG image and then we de-res it afterwards, we kind of have a good idea of what ground truth is there. So I think that's a challenge of dealing with this transfer of low res to high res and really of gaining good ground truth. And so that's actually the hardest part for us at SpaceNet, is how do we provide great enough ground truth to actually run an accurate competition that we think is fair. But definitely an area of exploration.
I'm not sure you actually need the exact chart sometimes for a lot of applications. Just knowing kind of a parking lot with X many square meters, Y square meters of cars are in it, and maybe accurate that, for example. I've done experiments where you can count cars on that set 30 meter imagery, because you have some other set not really allowing you to do that. So I'd love to see a challenge kind of set around something like that.
Definitely. Thanks.
Very interesting discussion. Let's take it to dinner. Thank you, everybody. This was a great evening.